All right, so we've been talking about our stack, and we've been seeing how the stack plays with the code that we're looking at, and we talked about escape analysis. We're starting to understand when something allocates. Remember, an allocation means that a value is constructed on the heap, not on the stack. That's what we'll reserve that word allocation for, heap. Construction. We've talked about escape analysis, but let's go back and talk a little bit more about our stack. There's at least one more thing that we have to discuss. Remember, the whole idea here is that we want to have potentially 50,000 Go routines if it's reasonable and practical to do so. And that means that every Go routine is going to have its own stack, and we wanted that stack to be very small. And we talked about that stack being small, starting out at 2K. 2K stack, right? But imagine the following scenario. Like, what's going to happen? You make a function call, we take a frame. You make a function call, you take a frame. You make a function call, you take a frame. Eventually, you're going to want to make that function call, and there's going to be no room left on the stack for that. Now, we can't just shut the program down because the stack was small and that's it. So what Go is going to have to do is grow the stack, right? And the way the Go compiler does that today, okay, the way the code is generated today is that we use contiguous stacks. And we're going to talk about how important contiguous data is at some point here in this video. But right now, what the contiguous stack means is that the function call that you just made that can't finish because there's not enough room here on the stack for that next frame, it's going to go out now and it's going to take a small cost and it's going to double the size of your stack. So we're going to go from 2K to a 4K stack, but it's a brand new contiguous block of allocation. And what does that mean? It means now that we're going to have to reframe everything that's currently there. Now, what's interesting is let's say we had a scenario like this on the original stack. Maybe we had a value here on this frame. We were sharing it down the call stack, which is totally cool. We now run out of stack space, and then what happens? Well, as soon as we run out of stack space, we now allocate that new twice as large stack, but these values have to come over. So what's happening now every time we have this sort of stack growth? Well, values are moving. They're moving. And for me, this is one of the very first languages where a value on the stack actually was moving around. It's a really interesting idea. But again, nothing is free around engineering, right? If you wanted to start with a small stack, because that's super important, right? Resource management. But you need to grow it. You've got to do it in a few different ways, and Go is going with the contiguous memory model here. So that means that these values are potentially moving around in memory as that stack grows, and these addresses here have to get adjusted, but that's really no big deal. But imagine the following scenario. Imagine that we had a Go program with 50,000 Go routines. Here they are, all 50,000, right? These are 50,000 stacks. And imagine we allowed Go routines to have pointers to stacks. Imagine we allowed this. All of a sudden, everybody's able to share values with everybody else, not just on the heap, but between these stacks. And now suddenly, one of these stacks have to grow. Maybe this one has to grow. We're going to move it over here. What does that mean? It means that all of these pointers that were going here now have to come here. We want to talk about stop the world latencies while we adjust 50,000 stacks and pointers. It wouldn't work, right? It doesn't work. And so one of the constraints of having a small stack that grows in this contiguous fashion is that no Go routine can share a value with another Go routine that's on its stack. So any pointers that we're going to have associated with the stack would be internal pointers for that Go routine and that Go routine only. And this would be another reason for an escape. If two Go routines need to share a value, then that value is going to have to be on the heap. We can't, again, be doing this kind of stuff. Remember, value semantics are very powerful. They give us that isolation model. They allow, mutation to happen in a very safe way. We get data locality that we're going to see is important. But the inefficiency of it all sometimes requires that pointer semantics to keep the complexity down, right? And here's another situation where we really need to leverage our pointer semantics here to keep that complexity down. But I want to show you this real. I want to show you this code live and show you a stack that's growing. So we're going to take a look at this code here. In this particular piece of code, we're going to have a constant of size 10 on line 9. There it is on line 9, constant of size 10. And what we're going to do is we're going to model this exact stack that I have right here on the board. We're going to model this in the code. So our string is going to be this value right here. That's our string. And what we're going to do is we're going to share that string down the call stack. We're going to share it down the call stack. In fact, we're going to share it down the call stack 10 times. And as part of sharing it down the call stack, we're going to end up having an array of size 10 ints, which is going to be 40 bytes here on the playground. Now, this is going to make for a very small frame. And so making 10 function calls right now with a 40-byte array is not going to be a big deal. We're not going to blow past the 2K stack size that we have. So if I run this code, and notice what this code is doing, it's going to display the value, display the address of things. Then 10 times it's going to call itself, and we're going to keep producing this type of stack model. If I run this, what you're going to see is on every single call, that value right now, that value that's up here, right, is at address A7, A8. It never changes throughout the call stack because we're not blowing past this 2K stack space. But what if I say, let's not use a 40-byte array, let's use a 4,000-byte array. Whoa, 4,000. I mean, on the first call alone, we're not going to have enough stack space. On the first call alone, we're going to have to double that stack, and a couple more times as well. So watch what happens now when I change the stack to be 4K, or not the array to be 4K. I want you to look on indexes 2 and indexes 6. And what you're going to see is the address. The address of this string value right here has moved. In fact, it's moved again a couple of times. And you can see that this is exactly what's happened. So you're seeing here how the compiler is setting up that code already for us. So if we don't have enough room on this stack, we're going to get a new one. Addresses are going to change, and those pointers are going to be fixed as part of that function call. Yep, maybe you're thinking, well, Bill, that's going to be a small performance. And I told you integrity always is going to require a little bit of a small performance. So we're talking about nanoseconds here. This isn't going to be the reason why your software is running slow. It really isn't, right? There's going to be other things, but I just wanted to show you how this stuff is real.